The Prac, the Prac set is on, obviously. It's about electroplating. So if you've watched the video, we're talking about electrolysis and we're talking about using electrical energy. So really important that electrolysis is using electrical energy from somewhere else. It's not creating electrical energy that we'll see a bit later with galvanic cells. We're using electrical energy to force a redox reaction to occur. Okay, that wouldn't happen naturally. All right, it's requiring energy for it to happen. So we're going to pump energy into it, and we're going to, in this case, we're electroplating with copper. We're going to be trying to put metal onto a surface. Okay, so that metal is going to come from ionic form, and all metals in the ionic form are going to be positive ions. Okay, so sorry.
Can you get negative ions?
Not for metals. Yeah, you won't have a negative ion on a metal. The metals are all going to be deficient in electrons when they're in ionic form. And that's how we find most of our metals in the ground, in this ionic form. So copper, you can find native copper. It's called native copper. You can dig it up from the ground, which is actually copper metal. It's not very common. It's not what's mined. Okay, you'll find it in mines. Sometimes there's a bit of an extra part, but mostly you're going to get copper minerals. And they're going to be, it's either be copper 2+ ions or copper, you can get copper just 1+ ions as well. Okay, now that's the same with most of them. Zinc, iron, lead, they're all going to be positive ions. They're connected to something else. They're connected to minerals, but that's that ionic bond. They are the positive ion, the cation. So we want to change that. We want to put electrons back on and cause it to turn back into metallic copper in this case. Okay, but in the normal general processing, we want to do that for all of our metals because we want them in metallic state where they don't exist in that state in the ground. So in our Prac, we are looking at depositing a metal onto a surface, and we do that quite a lot for certain different metals to protect them in some cases. Okay, cheap jewelry can be like gold plated or silver plated rather than being completely gold or silver. We can plate lots of surfaces with that, and we can use electrolysis in most cases we use electrolysis to do that. So the question, I suppose, is saying what factors might affect how much metal is going to be deposited. Okay, and so you have to first deconstruct that idea, but to do that, you really need to sort of think about, okay, well, what's the actual, what's the process going to be? And what are we doing here? How do we make that work? Okay, so I don't think there's a diagram here, but I'll do it on the iPad in a second. What we're going to set up, though, is an electrolytic cell. So we'll set it up with just one of the power supplies that we have in the lab. We can vary the voltage. Okay, we're going to connect the positive lead or the positive terminal to one electrode and the negative to the other electrode. Really importantly, it has to be set to DC current, which means that the current is flowing the same way the whole time. If you had alternating current, then the cathode and the anode would just continuously be swapping, and that wouldn't be any good. You'd get some chemical reactions happening, but they'd be happening at opposite sides and continuously changing like 50 times a second. So we want that to continue the same way around. So what we've got here is some information. It says it's known that passing electrical current through an aqueous copper sulfate solution, so nothing very fancy, just copper sulfate, the blue copper sulfate that you will have used in other years as well. But in copper sulfate, we have copper 2+ ions. Okay, we're also going to have the sulfate ions. Okay, however, the sulfate ions themselves, they're going to be negative. Okay, so potentially something might happen. Okay, but the sulfate themselves aren't very likely to occur, so it's probably likely to be water. But that's reacting at the other electrode. So we've got the copper ions, okay, and if we actually use, doesn't tell us that we're going to do that here, but you could, but they're sort of suggesting it by looking at the formula there, is that the two electrodes that you're going to use are both going to be copper electrodes. Okay, so what that does is it allows the reaction at both the anode and the cathode to be involving the copper. Okay, it does a couple of things that's advantageous to us, really. Where is the copper metal going to be deposited? We can read it off here and see that at the cathode, okay, we have copper ions plus 2 electrons are going to copper. Okay, now a couple of things that are really important. Like I said, if you've watched the video, one of the things to remember to help you know which one's going to be called the anode and which one's going to be called the cathode. Reduction, the reduction a half equation, the reduction part of the reaction is at the cathode. We often say like red cat, okay, to remind us what it means. What I don't want you to do is to commit to memory that cathode is negative. The reason I don't want you to commit that to memory is when you get to the galvanic cells, where it's actually producing electrical current, like it's acting like a battery, those charges are opposite. But reduction is still occurring at the cathode.
Are we supposed to be measuring how much copper builds up in the electrode?
Well, that's, if you go back to the, that's a good question. What factors might affect the mass of metal deposited? So you're going to be investigating in this electrolytic cell what can be varied to affect how much mass is going to be deposited there. So perhaps you could say, the more mass, the more effective it is. I mean, that doesn't really matter. But how can you what can you vary and what effect does it have? So there's more than one thing you can vary. I mean, I think it's fairly straightforward to think, okay, well, I could, I've got a power supply, I could do it on 2 volts, or I could do it on 4 volts, or I could do it on 6 volts. Okay, you could change concentration of the copper ion. So there's some different things that you can try automatically. When you're doing the deconstruction part, you should be thinking about all of those and sort of planning out and saying, well, what factors could affect? These are the things that it could change. What effect might they have? What do you know from, what can you sort of suggest from those ideas? If you've got more copper, does it make a difference? If you've got
do
more...
it normally first, and then we do a change to show the difference.
Well, I guess the thing is, what's normally like, so what you would be doing is, let's just say the simplest one to do perhaps would be to change the voltage. Okay, so what that's doing is changing the potential difference. It's easy to probably do as a prac, but you do have to think about how am I going to explain what changing the voltage does. Okay, so you might have to do some research behind what that means, but you would then run it for however long you decide, and that's something you think about, and you control that, make sure that was a controlled variable. It's always run for exactly 10 minutes, or it's always run for 5 minutes, and it might be a case of experimenting first and running it for a minute and seeing what happens. Like, you might get nothing, and you might say, well, I need to run it for 10 minutes each time, or it's so small a change in mass I can't measure it, or whatever. So that's part of the experimental process.
So say if you did one experiment where you're using 1 volt, and another experiment where you're doing 3 volts, you can compare the mass.
Yeah, and exactly, that's exactly what you would do. And the things that you always consider are, what did I have to keep the same each time? So in that case, you would have to keep concentration the same and all those sorts of things. There'll be some things that are hard to keep the same, because if you're going to run it once, then your electrodes are going to change the next time you run it. Do you then say, right, well, I'm going to clean it down, what do I do to... All of those things are part of your deconstruct. You write all the things that you can think about for it. So think about running break the problem down first and come up with some ideas, then go, right, well, this is probably what I want to investigate the most, and then you start writing a bit of a plan for it. So it's like a plan for it. So it does say here, deconstruct the problem to determine the most appropriate method for your investigation. Justify your method. Okay, and it does say trialing your design. So that's part of it. So we'll actually say that part of the design process is actually running it initially and saying, well, 1 minute or 10 minutes or whatever wasn't going to be appropriate, or this concentration was too low, I then adjusted what I did to change it so that I got some results, because you have to be able to measure some mass, okay? Otherwise, you're not going to get any results that are useful for it. So there is a bit of stuff here, a couple of things about electrolysis, okay? And it says that the mass of any element deposited during electrolysis, so the amount that's being deposited, is directly proportional to the number of coulombs of electricity passed. Now, for those in physics, which is only one of you, that coulombs is not a problem. For the rest of you, you probably go, what the hell's coulombs? You might have done it last year in physics. You might have talked about it in chem a little bit. It's really just a measure of how much charge, how much current, which is ultimately how many electrons are being passed through that circuit. And if you start thinking of it from that point of view, it makes sense, because if it's counting how many electrons, realistically, sort of how many electrons are going around the circuit, well, that's what chemistry is about, how many electrons are being passed on. And the only way that that can complete a circuit is if at the cathode there are electrons being used up off of the electrode, if you like, but then they're being transported by ions within the solution and then deposited at the other side. So to make that circuit, it is that the number of electrons that go around relates to how much mass or how many chemical reactions, if you count each chemical reaction as being one, must happen. And that the mass of an element deposited by 1 Faraday of electricity, okay, which we don't use as much in physics, is equal to the atomic mass in grams of the element divided by the number of electrons required to reduce one ion of blah, blah, blah. Okay? That is all very technical jargon for something that, if you think carefully about the fact that if we look at these two equations here, at the cathode, for every copper ion that comes over and touches the cathode, because the cathode has this excess, it has this energy in the electrons, that means the electrons would like to jump off that cathode if they could. Okay. Now, they're not going to jump off the cathode because they can't just jump out into a solution. But if a copper ion comes along, it's happy to take on 2 electrons. Okay. And because it's bringing this extra positive charge, it's like those 2 electrons, they haven't disappeared from the the electrode as such, but there's more electrode now on there, if you like, to compensate for them. So for every one of these, 2 electrons have been used up. Okay. Now the anode, because we've got a copper anode as well, a copper metal anode, and there's a copper solution, what can happen is that at that solution we can get electrons being left on the anode, on the electrode. Okay. And copper ions, so the rest of the copper atom, except for its 2 electrons that it's leaving behind, that goes out into solution. So for every one of these has to happen. Okay, because what has to happen is inside of that solution, there has to be still the same charge. You can't charge up a solution. Okay, so if it's happening here, then the same has to happen there. So for every 1 copper that is, if you like, put into solution and at the other side come out of solution, for 1 copper, that's 2 electrons that must have passed around the circuit. Okay, because each one requires 2 electrons or deposits 2 electrons. So for another 2 electrons, then another one of those occurs. So it's proportional. It's in relation to each other. Okay, so the copper at the anode releases copper ions and electrons, okay, which move into the solution towards the cathode. All right, we've explained all that sort of stuff there. What we've got, though, is some information about charge and current and that sort of thing. So the charge, C, is in coulombs, but it's equal to the current times by the time. Now that tells me something, or hopefully tells you something. On those power supplies, the thing you change is voltage. Okay? It doesn't tell you how much current is going through that circuit. So something, if you want to do something along those lines, you need to put something in the circuit that can measure the current. So we'll get a multimeter that can measure current and put it into the circuit so it can read directly, digitally off, this is the current that's coming off. Okay, and that current is in amps, and we multiply it by the time. What that really tells you is how many electrons go through the circuit. Current is how many per second. So if we multiply it by time, we get how many of those the electrons are traveling through, and we get that in what's called the charge in coulombs, because we don't measure it in the number of electrons, because it's a little bit like moles. If you'd said how many electrons went through a circuit, it would be in the, this stupid long number. Okay, so we measure it in what we call coulombs. Okay, very similar process, same idea as moles. Okay, so the moles of electrons, okay, and that's what we call Faradays, which we don't use in physics, okay, but that's like another unit we can use. So the moles of electrons is equal to the charge divided by this value here. Okay, and let's not worry about why that's the case. We're just going to use that value. Okay, so the moles of copper is the moles of electrons divided by the ratio. Okay, the ratio is 2. Okay, what it's saying is that for every one, every 1 mole of electrons, okay, we're only going to be able to do half a mole of copper, because each copper needs 2 electrons. Okay, so that's not written very well in this. That doesn't really, it's not that divided by that equals 2. It should have been that moles of electrons, that should have been, is divided by the ratio. Maybe if I put that into brackets or something to make it look a bit neater, which is actually dividing by 2. It's only dividing by 2 in this case because each copper needs 2. If it had been like copper 3 plus, which doesn't exist, but if it was copper 3 plus, we'd be dividing by 3 because we need 3. If it was just copper plus, Cu plus, you would just divide it by 1. It'd be 1. For every 1 electron, you get 1 copper. Okay, that's what that's saying. All right, saying how many moles of electrons divided by that. And then we can work out the mass by just using moles equals mass over molar mass, like that. Just written it, rearranged. Okay, so they've got an example calculations. If the current is 0.2 of an amp and the time that you ran it for was 5 minutes, then the amount of charge is going to be 0.2 of an amp times by, now that's in seconds, so 5 times 60 seconds. Okay, the Faradays, which is the moles of electrons, the number of electrons, okay, is going to be that value divided by this 96,500. Just take that for gospel. We're not here to explain all of those things, but it's divided by that number. So then the moles of copper, because the moles of, Faradays is just the moles of electrons. Okay, well, the amount of copper, the moles of copper, is half that, because we need 2 for every 1 copper, 2 electrons for every 1 copper. Okay, get that. That is then the number of moles, and then mass we're getting by doing it by the molar mass of copper, which must be 64. I can't remember copper off the top of my head. Is it 64? Looks like it's 63 something. Yeah. So that's your molar mass of copper, and that's the mass. Why would you do this? Because this gives you the theoretical amount that you should get. We're doing a prac. There is no way in hell you'll get that. You'll get a lot less. Okay? Or you'll get a reading that's higher, because when you weigh it, something contaminates the sample. It's not completely dry because it's come out of there, so you're weighing some of the water that's still there. All of those things are going to cause problems. But by having a question there, an example of what it should come out to be like, the theoretical value, you've got something to compare with when you're writing your prac. How close was I to what the theoretical values were? Where could errors have crept into it? Okay, so you could do it by changing the charge. And the way we would change, the current, you could think about how you're going to change that current. Okay, you could try by changing the voltage. You could change, the concentration of the solution. And if you think about this calculation, notice there's nothing in there that talks about what was the concentration of the solution that was in there. Okay, maybe that doesn't make a difference. Maybe it shouldn't. I don't know. Maybe there's a limited, like once if it gets too low amount, then it won't conduct the electricity as well. okay? But you'll want to be able to measure that current, okay? So what do you have to do? You need to deconstruct the problem, okay? So you've all done deconstructs in other subjects. Importantly, you've got 4 pages, all right? Not 4 double-sided, so a maximum of 4 A4 pages to do it, okay? You should absolutely consider using concept maps, flow charts, tables. Tables in particular are good because you can summarize data. Dot points. It's not an essay. It's not a report. Okay, it's information. Okay. 2, 1, deconstruct your ideas. 2, propose a method. Okay, but also justify that method. Okay, why would you do this? Why are you going to do that? And part of that might be, oh, well, this is the method that I want to do, and I quickly set up the experiment, and I decided that, for these reasons, this was the concentration I was going to use, or this is how long I was going to run it for because of those things. It might still be that when you do the prac, you change it again. You might, that's perfectly fine. Okay. So you have your 4 pages. There's no word count to it, but it's not like you try and cram, 4,000 words onto 4 pages. That's not what it's about. Okay, use diagrams, tables, dot points, anything like that to deconstruct and then plan it. So it's deconstructing the thing and think about all the different things that you would need to consider, and then come up with a plan for the actual prac itself. Now I haven't sort of shown you. Did you last year do anything with these sort of cells where you plug a power supply to it and nothing like that at all? No, that's okay. So perhaps tomorrow I'll get some stuff out, just sort of demonstrate, so that it's a bit more clear in your mind about what we can do with it. Okay. Probably just use copper and just show you. Okay. Because some of the things that you want to be aware of is when you do it, the copper, unfortunately, in this situation, is not going to deposit onto that onto the cathode in a nice, smooth, hard form. Okay, in this set, to do electroplating like that, they have other parts in their solution. They do it at certain conditions and stuff. It's basically going to be lumps of copper that are going to form, and in fact, some of them will probably fall off and sink to the bottom of the solution. So that's going to be part of our process of okay, how are we going to make sure that we collect all the copper that's on that side? How do we make sure that we know that that it's occurring? One of the things maybe you should consider is, because we're doing copper on the other side, for every copper that's deposited, a copper should have been taken off the anode. So perhaps the loss of mass of the anode could be a better reading than what the gain of mass at the cathode is going to be. Because if it's losing mass, that's a whole lot easier. Nothing's collecting there, it's just getting smaller. And all things being equal, those 2 numbers should come out the same. For any, for 1 gram of loss on one side, 1 gram should add on the other side. Now we're not going to get up to grams an ounce stuff, but it's okay. So I would suggest, though, you do also weigh the other part too, so you can compare it. So once you have, once you've sort of come up with that, okay, it's your design is part of this 4 pages. So this investigation design is part of that 4 pages. Okay, so you need to put all of that stuff down, including safety considerations, all that sort of stuff. So 4 pages to cover the deconstruct and this design. Okay, submit that for teacher feedback. Effectively, there's only 5 of you anyway, so I'll work with you and make sure that's okay. Then you're going to do your prac, and from once that part there, you can sort of consider that, right, that part's done. Then the prac is just a normal written up prac. Okay, this one though, in comparison to the first one you did, this one's going to have the hypothesis. It's going to have a independent and dependent variable. You're going to change something, vary something, see what effect it has. Okay, what effect is the rate going to be? If you think about what we've talked about, and when we look at the prac tomorrow, my computer's about to turn off, then hopefully you will consider, I think I can stop it, hopefully that you can consider that there are some things that perhaps shouldn't change, but obviously maybe will. So something we haven't talked about is how close are the electrodes to each other? You know, can you imagine if you set this up in a massive like swimming pool worth of stuff and you put one electrode 50 meters away from the other one? You know, is that still going to have the same result as when they're really close to each other? So you could vary the distance between them. That could be something else you could look at. Okay, so remembering that all of these calculations here are ideal world calculations. Okay, they are theoretical perfect. What we're going to look at is to say, well, what if we vary some stuff? What happens to it? Okay, but you can also compare to what your results are and what the theoretical results should be. Okay, so I do want you to be considering that. The rest of the stuff is the same as the other prac. Right, I'm just going to switch this